Well, let's go ahead. Let's dive into the single layer perceptron. We're going to kind of talk about some nuances here, do some math. We'll go to the whiteboard. I'm going to show you how to kind of just think about a multi-layer perceptron from scratch. Think about it mathematically. And then I think after that, we'll probably take a little bit of a break. Okay? Before we kind of move on to the next portion. But with that said, let's go ahead and understand what are single layer perceptrons and the motivation behind them. Okay, so the idea behind MLPs. So MLPs are going to be multi-layer perceptrons. Okay, so MLP, whenever I say that, this is going to be a multi-layer perceptron. Okay. So MLPs are going to essentially allow for these nonlinear relationships between input and output variables. Okay. And the flexibility of these models, right, enable you to kind of do a variety of different tasks. Okay. So with MLPs, and MLPs, when you think about MLPs, y'all, these are going to be essentially the feed forward architecture. Okay. So multi-layer perceptrons are pretty much kind of the most simplest kind of case of a feed forward neural network. Okay. But with these MLPs, you can do things like classification, regression, you can do image classification, text classification, you can do all those different things that you can do with machine learning models, but we kind of do it in a basic kind of feed-forward architecture, okay? So the multi-layer perceptron is going to be the most simplest kind of feed-forward neural network. But before we talk about a multi-layer perceptron, we definitely want to talk about what are called single-layer perceptrons. These are essentially our neurons in the multi-layer perceptron, okay? So with these single layer perceptrons, okay, so a lot of math are going on here, but I don't want us to worry about too much about that. I'll kind of talk about, I'll give you all the highlights, okay? So these single layer perceptrons, okay, they have a bunch of observations. So that we have the input that are going to be kind of given here in this input layer, right? We have these highways of information that are connecting the neuron with essentially the output node. So in a single layer perceptron, there really are no hidden layers, okay? What the single layer perceptron is doing is it's going to go from input, multiply by the weights, and then get to the output, okay? And how is it going to do that? It's going to be given by this formula right here, which I'll write out for you here more in a second, okay? So the output, so for example, this is going to be our output, so y hat. This is going to be sigma, which I'll talk about what that means here in a second, but sigma of our features, our neurons, x1 times w1 plus all the way down plus xm wm, like that, okay? So our output, what's pretty much being done is we're going to take kind of like the input, multiply by the highways of information, and put those into a linear combination. Okay, this is what's called a linear activation. This linear activation right here, this linear activation, then is going to get fed into linear combination. My goodness, where's my brain at? Linear combination is going to get them fed into what's called an activation function. Okay, this sigma is what's called an activation function, and this sigma is usually going to be non-linear. Okay, now this is going to be a non-linear function. Now this sigma right here too, y'all, for a single layer perceptron, it's usually going to be kind of a binary output. Okay, so what do I mean by that? So sigma is usually going to be, so whatever the input is, so I call that input like z, for example, is usually going to be defined as follows. So it's going to be 1 if, for example, z is bigger than 0, and it's going to be like 0 if z is less than or equal to 0. If z is less than or equal to 0. But again, these cutoffs are arbitrary. So for example, if you want to make this like 5 and -5, we can do that. If you want to make it 5 whenever z is bigger than 7 and less than 7 here, you can do that too, okay? This sigma is usually just going to be kind of like a binary output, kind of a true false, okay? It's what's called like a sign function, okay? But this is kind of like the first kind of nonlinearity that's getting introduced into our neural networks, okay? Because remember, y'all, neural networks want to understand complex patterns, right? And in particular, nonlinear patterns, okay? We want our neural networks to understand nonlinear patterns, right? So we can kind of understand a lot of the nuance that's happening in our data, all right? And this sigma is how we kind of impart that nonlinearity to allow complex relations to be understood downstream, okay? Now, I guess you might be asking yourself, why does sigma need to be nonlinear? Right? Why does sigma need to be nonlinear? Well, that's a question I have for y'all, right? What do y'all think? If this sigma was just a regular linear function, okay? If this sigma was a traditional linear function, what are we really just doing here in our calculation? What do y'all think? Okay, and again, feel free to put this in the webinar chat. If sigma was really just linear, and we got an output, and we're trying to find the weights which get us that output, what kind of operation, what kind of mathematical operation are we really doing here that might look similar to before? What do y'all think? Very good, very good. Anybody else? Because remember, with single-layer perceptrons, we're trying to find the weights, we're trying to get us that output, right? So if sigma were just a traditional linear function, just regular linear, what are we really doing? Kind of like some ideas here. With a range of classification, probabilities, potentially. Yeah, there you go. There you go. Very good. So in this case, y'all, if sigma was traditionally just a linear function, right? What happens, right? If sigma were linear, look what happens. We're going to have y hat, and if sigma was linear, we're pretty much, it's just going to be some constant. So some constant, which I guess we can call like c, multiplied by x1, w1, all the way down plus xn times wn. Well, what we're trying to do here is we're trying to find the weights which get us the best output, the best w's, which get us the best y hat. Well, what is that? This is actually, as some of us said it, this is in fact just regular old linear regression. Okay? So this is something to keep in mind, okay, y'all? And this is actually a really good interview question, okay? This is why you need nonlinearity, because if you did not have these nonlinear functions, like sigma, for example, okay, what you're really just doing is just a really fancy linear regression problem, and that's nothing really new, okay? Or logistic regression, or however you want to talk about it, either the continuous or binary output, okay? You're really just doing a fancy regression problem, all right? And this is why we need that nonlinearity. We want to understand complex patterns. Well, you need to actually understand where that complexity should be inserted. And this is going to be where, one location where. Okay. So please keep that in mind. This is why we need sigma to be nonlinear. Because if it was linear, we're just going to do fancy linear regression. And that doesn't tell us anything new. Okay. That's a great interview question. So something to keep in mind. All right. So that, in a nutshell, is kind of a single layer perceptron. Okay, we have weights multiplied by our inputs, getting fed to a nonlinear function to get the output, and we want to find the best weights which get us the best possible output. Okay, so now what we want to do now is take this and pretty much beef it up, make a bunch of neurons kind of together, and combine them, and combine all their weights to make the best possible output that we possibly can. Okay.